Good day. Today we're going to be talking about Chapter 19, Prelecture 19, or about Lecture 19. In Chapter 19 we start talking about thermodynamics again. So it's kind of a review and then advancing on Chapter 5 from 1211. Okay, so we've talked about the idea of entropy, but it's going to come in a lot more. We're also going to bring back in Gibbs free energy and just look at those terms a little bit more in detail. So let's first just look at some terms within this chapter. We talk about a spontaneous process. So a spontaneous process is one that occurs without any outside influence. So this will be something that occurs whether or not you input any energy. Such as the rusting of a nail. It will occur without any outside influence. It occurs slowly, right? Because remember, thermodynamics, kinetics, not the same thing. But thermodynamically, a spontaneous process is one that doesn't require any additional input in order to occur. We also have what's called a reversible process. This process doesn't truly exist, but we use it as a simplification. So it's a process in which you can restore your system to its original state without changing the surroundings at all. So there's no heat transfer between the surroundings and the system. Okay. We also have an irreversible process. That's what we consider basically any real process will be an irreversible process. And this is one where our surroundings are going to be changed when the system is restored to its original state. Okay, and then we have an isothermal process. This is a process where the system remains a constant temperature. So iso, same thermal temperature. So this would be like a phase change, where we're staying at the same temperature, we're just converting one substance from one phase to, or a substance from one phase to another. So we're going to look at spontaneous processes a lot, and we think about a spontaneous process, or if we think about a spontaneous process, it's only going to be spontaneous in one direction. So if you have a reaction that is spontaneous in one direction, it will be non-spontaneous in the other. And we usually think about spontaneous processes being exothermic, but that is not true. Okay. Okay. Another thing we're going to look at in this chapter is our laws of thermodynamics. So we have a lot of different laws of thermodynamics. We looked at the first law already. Energy is neither created nor destroyed. Right, you can't make energy, you cannot destroy energy, it just exists. We're going to look at a couple of different, we're going to look at all four thermodynamic laws. So we looked at the first. We also have the 0th law, and that's if two objects are in contact at different temperatures, they will equilibrate to the same temperature. We've already kind of looked at that idea before when we looked at specific heat, right? So if we throw something hot into cold water, they'll both come to the same temperature. Okay. We're also going to look at the second law of thermodynamics. So for the second law, our entropy change is going to be greater than 0 for a spontaneous process. And we're going to look at why in class, but so if we have a spontaneous process, we're going to increase our entropy of our universe, where delta S of our universe is equal to delta S of our system plus delta S of our surroundings. Okay, and then we're going to look at the third law of thermodynamics, which is if we have a perfect crystal at 0 Kelvin, so a perfect crystal has no defects, it is going to repeat perfectly in all 3 dimensions. So what we looked at in chapter 12. So if we have a perfect crystal, and that perfect crystal is at 0 K, where we have no molecular motion, then we have 0 entropy. Okay. So, entropy itself, we've already looked at this, but we're going to look at that a lot more in detail. So, entropy is kind of a measure of disorder. So the more disordered something is, the more spontaneous. So we're going to trend towards greater disorder. Excuse me. So if you think about such as something like going from a liquid to a gas will have greater disorder. So going from a liquid to a gas increases disorder. Right? So even though going from a liquid to a gas is going to require energy, going from a liquid to a gas increases disorder, so this is a spontaneous process. Okay. If we are, or it's a spontaneous process above the boiling point of the substance. Okay. We're going to look at the change in entropy for phase changes. We look at that change of entropy of a phase change. By taking the enthalpy of that phase change in joules divided by the temperature in Kelvin. Okay? And if we have a delta S that is positive, that is going to be a favored process. And depending on temperature, it could in fact be a spontaneous process almost always. Okay, so we're going to also look at entropy in terms of microstates. So the more possible microstates, the more entropy. Which is why a gas will have greater entropy than a liquid, for instance. But let's look and think about what entropy, or what a microstate is. A microstate itself is kind of viewed as the possible arrangements of all molecules in a system at a single instance. So we can think about this. So let's take a tube or a glass ampule where we have two molecules. And we have two molecules, and this is under vacuum, and this is our stopcock. If we take this stopcock and we open it up, allowing the molecules to escape from here to there, we end up we end up with several possible microstates. So we can end up with our molecules moving there to there, there to there, right there. That one's. So we could have them move, they can switch, they can go in each way. So we have 4 of these. We have 4 possible microstates. And that's if we only have 2 molecules. As we increase the number of molecules, we're going to increase our possible number of microstates. Okay. So that is kind of, without going too much in depth, kind of a summary of what we'll be going over today in class. If you guys have any questions, please let me know. I'll see you guys later.